Okay, this section deals with chemical kinetics as it applies to the collision theory and transition state diagrams. So collision theory and transition state diagrams. Now, when considering the collision theory, we're talking about what is required for a set of particles to undergo a chemical reaction. For any reaction to initiate, is E start, four reaction factors must occur simultaneously. These four reaction factors can be reduced to a simple acronym CENT, where C represents an effective kinetic concentration. E refers to effective collisions. And has more to do with orientation of the colliding molecules. Certainly you must have naturally reactive reagents. And finally, the proper activation energy or temperature energy considerations or factors. Reaction. The process is typically illustrated using the Maxwellian Boltzmann distribution curve of a set of particles or reactant particles against the energy, that intrinsic energy or internal energy that they contain. I'll just reduce that to Boltzmann distribution of particle energies at a specified temperature. Now, given a graph of the number of particles versus the general energy content, of a quantity of particles, a large quantity of particles, and say in a typical chemical reaction, at say temperature low or temperature 1 or say room temperature, you might have a curve that would be represented by this graph right here. We'll call that T1. At a specified point represented by this red line, this point is referred to as the activation energy needed to initiate the chemical reaction. This is the point where all four reaction factors need to come together in order to initiate the chemical reaction. And this, of course, is equal to delta EA, or the activation energy. Now, the four factors all come together simultaneously at that point. So in the diagram that we have, the particles under this curve, or in the area under T1, have sufficient energy to generate products. However, if we heat this overall quantity of particles, then we can shift some of those particles that do not have sufficient energy across the activation energy line so that more particles can undergo reactions. So if we heat, we might generate a curve that would have this trend, like this, and we'll call that T2. Obviously T2 is greater than T1. Now we have the area under T2 along with the particles that were under T1 available for reaction. So everything under this T2 curve has sufficient energy in order to have the proper, assuming we've got a proper kinetic concentration, the particles must be able to find one another. Effective collisions, naturally reacting particles, and sufficient energy in order to generate the products that we're trying to produce. Now, this curve is represented by a mathematical expression derived by Arrhenius, and we call it the Arrhenius equation or expression. And has a form of rate constant is proportional to exponential minus delta EA over RT, where delta EA is the activation energy, as we noted earlier, R is the thermodynamic form of the universal gas constant, and is 8.314 joules per mole Kelvin, and T represents the Kelvin temperature. Now we need to apply the Arrhenius equation to two different temperature values, which would give two different rate constants. We'll simply say that temperature 1 has a rate constant K1, and temperature 2 would have a rate constant K2. So given the Arrhenius expression K proportional to e to the minus delta E sub A over RT, this can be illustrated as an equation by inserting a proportionality constant, giving us this expression, capital A as a proportionality constant, e to the minus delta E sub A over RT. Now, the consideration for K1 at T1 and K2 at T2 would allow us to equate the Arrhenius equation to the two conditions and solve a composite equation that would allow us to determine activation energy, rate constant at different temperatures given one set of conditions, and so forth. So for conditions number 1, the K1 and T1, K is equal to A e to the minus delta E sub A over RT1. And we'll call this, A is going to be the same for whatever. And this is K1. And K2 is equal to A e to the minus delta E sub A over RT2, like this. Now, if we solve each one of these for the proportionality constant, we will have A is equal to K1 over E to the minus delta E A over RT1, and we'll have A out of the second expression to equal K2 over E to the minus delta E sub A over RT2. Well, of course, A under either condition is unchanged as a proportionality constant. So if A equals A, then the relationships that we've derived for A are also equal. And so we can say K1 over E to the minus delta E sub A over RT is equal to K2 over E to the minus delta E sub A over RT2. And that one's 1. Now, what we wish to do is collect the terms containing the exponential and the rate constant terms on one side of the equation, so forth. So what we'll do is solve this so that we have a K2 over a K1 to equal E to the minus delta E sub A over RT2, and that's divided by E to the minus delta E sub A over RT1, like this. Now, in this relationship, we can take the logarithm of both sides of this relationship and have the natural log of K2 over K1 to equal the natural log of this entire expression, E to the minus delta E sub A over RT2, and E to the minus delta E sub A over RT1, which equals ln of E to the minus delta E sub A over RT2 minus ln of a minus delta E over RT1, like that. Well, the logarithm of the exponent is of the function E, or the base to the natural logs, is the exponent. So the first term, ln of K2 over K1, can now be equated to a minus delta E sub A over RT2 right here, minus a minus delta E sub A over RT1. Well, adjusting the, rearranging the, this expression on this side so that we have the positive listed first, we show it's as delta E sub A over RT1 minus delta E sub A over RT2. So now we factor out the delta EA over R, and we get the final form of the Arrhenius equation. And a more functional capacity here, in other words, more usable, user-friendly. Now, I like to use the expression in this form. And it's just preference more than anything, but it's a little easier to substitute and multiply and grind through the numbers. All right, now we have to apply the apply the equation to determine delta EA for a reaction. Say we are given acetaldehyde, okay, for a reaction. Here's the reaction: acetaldehyde CH3CHO as a gas decomposes to methane gas plus carbon monoxide. At temperature at T1 equals 759 Kelvin, we have a K1 rate constant of 1.05 times 10 to the minus 3 molar 1/2 times seconds. And the second temperature at 836 Kelvin will give us a rate constant of 2.14 times 10 to the minus 2 molar to the 1/2 dot seconds, like that. And the R value needs to be expressed in kilojoules. So R is published or reported in reference as 8.314 joules per mole Kelvin. But if we want the outcome to be in kilojoules per mole, we need to use 0.008314 kilojoules per mole Kelvin for the value of the R value. So if we take this expression, this term and this last term, and equate them, and then solve for EA, substituting the available data, we can determine the activation energy for the reaction. So let's do that. Ln of K2 over K1 is equal to delta E sub A over R, T2 minus T1 over T1 dot T2. So we want to solve this for E sub A, so delta EA is now equal to R Ln times Ln of K2 over K1 times T1 times T2. So we would divide both sides by this ratio and then invert and multiply it back through. And so this would be T2 minus T1 in the denominator. Now, substituting the available data, let's move this over a little, about right here. We'll have 0.008314 kilojoules per mole Kelvin for the R value times ln of K2, which is, and we'll make these equal so we can cancel them out. So I'm going to move the decimal over to the right one place. 21.4 times 10 to the minus 3 molar 1/2 dot seconds divided by 1.05 times 10 to the minus 3 molar to the 1/2 dot seconds. Like that. Of course, this will drop out very neatly, and we're left with kilojoules per mole after we cancel out the Kelvin values. Okay, then we need to multiply T1 and T2 to this. T1 759 Kelvin times 836 Kelvin. Right there, 759 times 836. And of course, that's divided by the difference in the temperatures, T2 minus T1. So T2 is 836 Kelvin minus 759 Kelvin, as the denominator shows. Now, you can simplify this through the logarithm, and we'll see what the results will give us. Now, extracting all the units associated with the various data, and knowing that the results is going to come out in kilojoules per mole, I can reduce the computation to something a little more friendly, user-friendly, and so we substitute into the calculator to generate the final activation. This gives 206.54 kilojoules per mole, and for simplicity, we'll round that to 207 kilojoules per mole and just use three significant figures. Now, we're not quite through with the problem. It wants us also to calculate the what the rate constant would be at a higher temperature. Back up here. Okay, simplifying it, using the delta EA equals 207 kilojoules per mole from the previous calculation. Calculate the rate constant at 865 Kelvin. Well, from the Arrhenius expression or equation, we have a K3. My apologies. Let's see. Let's call that K3 instead of a K2. Now, K3, of course, will be the 865 Kelvin. So K3 is unknown at 865 Kelvin, where K1 is equal to 1.05 times 10 to the minus 3 molar to the 1/2 dot seconds, like that, at 759 Kelvin from the previous problem. And we already know that the activation energy, delta EA, we're going to use 207 kilojoules per mole, and again the R value expressed in kilojoules, 0.0081314 kilojoules per mole Kelvin. So we want to substitute the appropriate values into the Arrhenius equation and solve for K3. So we can solve for K3. So ln of K3 over K1 is ln of K3 minus ln of K1, which equals delta E sub A over R T2 minus T1 over T1 times T2. Then we can solve this for ln of K3 to equal ln of K1 plus delta E sub A over R times T2 minus T1 over T1 times T2. Now, keeping this as simple as possible, we have ln K3 to equal ln of K1 1.05 times 10 to the minus 3. Now the units are going to come out at the end of this molar 1/2 dot seconds, just as they have in the first problems, plus 207 kilojoules per mole divided by 0.008314 kilojoules per mole Kelvin, and then we will have T3, right there, and right there, where T3 is 865 minus 759 over 865 times 759, and we'll substitute that into that parenthesis right there. So now, simplifying all the units and removing them, we'll have ln of K3 to equal ln of 1.05 times 10 to the minus 3 plus 207 over 0.008314 times 865 minus 759 divided by 865 times 759, and we want to solve that and then take the analog of the ln function. So now this gives us the logarithm of 1.05 to 10 to the minus 3 plus 4.02, with simplifying that part of the equation. Now the logarithm of 1.05 times 10 to the minus 3 is a minus 6.86, and we add back to that a plus 4.02, which leaves us with a minus 2.84, which is equal to the logarithm of K3. So when we look at the logarithm of K3 to equal a minus 2.84, then we can take the analog and get the new rate constant to equal e to the minus 2.84, and this is 5.84 times 10 to the minus 2 molar, square root of molar times the seconds. Okay, I'm going to put this in a separate video under transition state diagram.